Okay, so today is our lecture 15. And before we start our materials, I want to talk a little about the final project. So I got several inquiries about the project ideas. And I would say that our project is very open-ended and it's very flexible. So your idea could either be biological or computational. And you have that data set we gave you, and you can also supplement it with other additional data sets you found useful. So you have a lot of flexibility in designing your project, but the key is to show your knowledge, your novelty, or your hard work. So either is fine, but it's important that you just don't copy what's already in the paper. Data set is from a benchmark paper. So what has been said in the paper is already there. So repeating these results will not be so interesting. That's something I would say. And also, if you just run the standard SURAP pipeline as on the SURAP website, that's also not considered to be very novel or innovative. So just try to show your novelty. Yeah, I would say that's just my overall suggestion. And it could be biological, it could be computational. And I have seen some interesting ideas from your emails already. Yeah, so if you can find something related to your current rotation project or the labs area you want to work in, that would be great. All right, so let's continue our discussion about linear model. Last time we spent quite some efforts talking about the general setup of the linear model. And then we talk about the generalized linear model. We said that linear model can be regarded as a special type of GLM where the random structure is normal distribution. While in GLM, the random structure could be Bernoulli, could be Poisson, or it could be negative binomial. So you can have more distributions to be assumed for your response variable. But no matter what, so you always want to link the expectation of your response, which we call mu I, the expectation of yi, in some way to a linear function of the features or predictors. So here the features are something you have already obtained, and you want to show how each feature's value would change according to, or is how each feature's value is associated with the value of the response. So under the Poisson regression or MB regression, for example, you are basically assuming that the log of the mu I is a linear function of the features. And under the logistic regression, you're assuming the logit of the mu I, here the mu I is a probability between 0 and 1, is a linear function of the features. And under the linear model, you directly assume that mu I is a linear function of the predictors. So these are what we call the systematic structure of GLM. But ultimately, your interested parameter will be beta, because beta reflects how the predictor, how the change in each predictor's value would be associated with a change in the mean of the response after transformation, of course. So today I'm going to add one more thing about the predictor. So we know that the predictor can be numerical or it can be categorical. These are often very common in building a generalized linear model. By numerical, I mean, okay, a predictor may be a person's income, or in our case, maybe a gene whose expression values are measured. So in that case, it is a numerical predictor whose values are meaningful. So like 1, we know, okay, in the linear model, if you change the value from 1 to 2, it's the same as if you change the value from 2 to 3. So that's what we call linear, right? The same change gives you the same effect. But in some cases, the predictor could be like race, gender, or it could be country, region. In those cases, it is a categorical predictor. Then how do we use those? So in the GLM, for a categorical predictor, let me just make it easier. So if we have a categorical predictor, or we often call it a feature with, say, capital K levels. So for example, like it could be, let's say in bioinformatics, we could say it is like k different experiments. Okay, so experiment batch, we measure in k different batches. So we want to account for batch effect in our modeling. So therefore, it is reasonable to include batch as a predictor or feature in your linear model. Then how do we encode it? So although we can surely encode the batch as batch 1 to batch k, but here the labels do not mean numerical, do not have numerical meanings. That is, going from batch 1 to batch 2 is the same as or I wouldn't say the same. So there's no guarantee that, okay, the difference between batch 1 and batch 2 is the same as the difference between batch 2 and batch 3. So which means that here the numerical labels should not be taken as numerical values. Then how do we encode them? The common approach is that we would encode such a predictor as k-1 binary predictors. So what does it mean? It means that, so for example, if observation I is in batch 1, okay? So then what do? We will take batch 1 as the baseline. Is the baseline, or sometimes we call it the reference level, which means that in the k-1 binary predictors, we start from batch 2. So let's say in this case, then we can write it xi as a vector with k-1 dimensional. So this corresponds to batch 2, 3, up to batch k. So because observation I is in batch 1, so then its corresponding binary predictors will have value 0 throughout. That's the case. And if it's in batch 2, then we will encode it as 1, 0, 0. If it's in batch 3, then we will have 0, 1, 0. And if it's in batch k, we would have 0, 0, and the last one is 1. So you see, using the binary encoding, we will be able to exactly code the batch each observation is in. That's what we are going to do. And correspondingly, because now we convert this predictor into k-1 numerical predictors, then we would have correspondingly k-1 coefficients, each associated with batch 2 to batch k. So you will see that we will have k-1 coefficients. So if I denote them as beta 2 to beta k, then what will be my model? So assuming that I only have this one predictor or feature in my model, then my model based on this, the linear model, how I wrote it, you see, so it will basically be, I can write it as, okay, I can write it as yi equals beta 0, that's the, beta 0, that's the intercept for the baseline, plus, okay, so given the notation I wrote here, I can write it as xi transpose, so this row vector times beta 2 to beta k plus epsilon I. And since this is a linear model, I would assume linear model, the random error terms are IID, normal, zero mean, variance sigma squared. That will be my linear model. And if it's GLM, so if this is a linear model, right? And if it's a GLM in general, then I would assume that yi follows some random distribution. They are independently following some distribution with mean mu I, its own mean mu I. And then I will have some transformation I call the link function G applied to mu I. This is assumed to be the linear part. So it's equal to beta 0 plus xi transpose beta 2 to beta k. So same. So what I mean here is that essentially to include a predictor with k levels, you are essentially introducing, so include a categorical predictor with k levels, you are essentially including k minus 1 numerical predictors with k minus 1 slopes, k minus 1 coefficients. So what this actually means, this model? If we look at this, so essentially we are basically having a different intercept for different levels. That's the model we're having. So let's say this is G mu I, the transform mean. And what this is saying is that, and this is just like the ith observation, okay? So what this means is that if the I equals, okay, if I equals, let me think. Probably I should say, this is the bad way of encoding it. No, I don't think this is good. So I don't need the x-axis. I just need the y-axis, okay? I don't need the x-axis. Basically, what I want to say is that, so if the observation I is in batch 1, then here on the y-axis, what I have is beta 0. So that's the intercept I have here. So the mean will just be beta 0. And if the I is in batch 2, then I'm going to have the intercept or the expectation G mu I as beta 0 plus beta 2. And if it's in batch K, it will be beta 0 plus beta K. So essentially what I'm having here is that for each batch, I'm shifting its intercept. The reason I just have a point here is because my only predictor is the batch. I don't have other predictors, so that's why I don't need the x-axis. If I have another numerical predictor, then I can add it as the x-axis, then I'll have slopes for the effect with this predictor. So this is what we say. So essentially for a categorical predictor or feature, once you include it, you are essentially assuming, yeah, my different batches give me different intercepts. So this is something to keep in mind. How do we incorporate a categorical predictor into a linear model? And also it is important to remember that in a linear model, what is required to be continuous and real valued is the response. It is not a feature. Some people just mistook this concept by saying, okay, the predictor must be continuous, but that's not the case. The predictor could be categorical. And we actually have a name for linear model with categorical predictor, and that's called the ANOVA. ANOVA analysis is actually for this case, a jargon for this case. Okay. That's the linear model with categorical predictor, and same thing for GLM. So now I'm going to tell you a little bit about what we call the linear mixed effect models, LMM. And actually in my other class 205, I spent quite some time to talk about this. So we will just give a very brief introduction here from the application perspective. But if you are interested in checking out more, you can watch the video from the other class. So the linear mixed effect model, LMM, by name, it stands for, there is a mixed effect means that there is a fixed effect term and there is a random effect term. And you incorporate them into one model and call that mixed effect. So what does that essentially mean? So for the fixed effect, it means that, okay, the slope coefficient is considered to be fixed. And for the random effect, it means that the slope coefficient is considered to be random. So when do we need to do a model like this? This is for the case when our data has a clear group structure. Observations belong to many small groups. So for example, in biomedical research, the groups may correspond to subjects like patients. So for example, let's say that I'm going to quickly show you an example by screenshot later. But what I want to say is that in this case, let's say if you want to study the effect of a treatment on like the clinical outcome. So Y would be your clinical outcome, some continuous measurements, and X is a treatment. And you want to see how this treatment affects the response. But here you are measuring people, multiple people. So each person has multiple measurements. And you definitely want to include the subject as a factor into your model, right? You don't want to leave that out because the treatment may have bigger response in some patients, but smaller response in other patients. So we want to take that into account. So in this case, let's say that we have patient or subject I that go from 1 to n. So we have n people, but within each people, we have ni measurements, of subject I. So then we can say this is I from 1 to ni within subject I. Okay, and then we do have the measurement, say Yij is the response. So for example, this is the clinical outcome. And we have Xij, which is also a scalar. This is just the treatment. The treatment the treatment in the jth measurement of the ith person. Okay, so then our model would be Yi equals, of course, we are interested in the treatment, right? We might wonder if there's an intercept, we call beta 0 plus the treatment effect, Xij beta, plus epsilon ij. We will do that. So here the j go from 1 to ni, I go from 1 to n. But this seems to be problematic because neither the intercept nor the slope seem to be dependent on subject I. That's not something we believe it should be, right? Different people may have different baseline and they may have different effects. So therefore, maybe I call this beta 1. So a more reasonable way is to call this beta 0i, beta 1i, to give a sub-index I, to mean that the intercept and the slope are both specific to subject I. Intercept and slope are subject specific. So you see, if I do this, I'm essentially, if I do this, this is equivalent to that I incorporate subject as a categorical predictor into my model. Use subject I from 1 to m as a categorical predictor in my model. So I could do it this way or this way, and they are actually equivalent. So fitting N regressions, right? This means that I fit one regression per subject. And this is essentially equal to that I fit one regression for all subjects, but I consider this subject as a predictor itself, and subject has an interaction with the treatment. Okay, so what I mean is this. So this is equivalent to this model, that is Yij equals to a common slope, I call beta 0, and a common intercept and the common slope. I call it here. And that also includes the subject. Okay, so I have it. So plus the, let me think of it. The indicator, okay, indicator that I equals to the second subject times beta 2 plus 2, the indicator whether it's equal to subject M times beta N, right? So this is how I encode it as a binary, a set of binary predictors. Is it 2? No. Or yes? Is it 3? Yes or no? Is it N? Yes or no? So I have introduced those slope, those coefficients. So you see, these are essentially modifying the intercept, because whenever one of them is yes, this is added to the intercept. And then I can have the interactions, that is xij times indicator is I2, right? And then I can have this called beta 1, 2. And probably I call this beta 0, 2, beta 0, m, you see. And then I can do plus plus xij times indicator is I equal to n times beta 1, m. And then finally, the error term for sure. So you see, what I mean is that this model and this model, they're the same. Because for each subject, it's going to have its own intercept. Okay, so you can see, so if I is equal to 2, then the intercept is essentially beta 0 plus beta 0, 2. That will be the intercept. And if it's the I equals 2, then the slope is essentially beta 1 plus beta 1, 2. This one plus this one. So you see that I still have every subject with its own intercept and its own slope. So that is exactly equivalent to what I have here. So it's just two ways of writing down the same thing. It's just that here I just do this for a specific I. But what I wrote down here is the general term for all the I's. Okay, so what I mean is that you could fit N regression lines in R if you do coding. So this means that you do N regressions. And what you do here is that you just do one regression with all your data and you're done. And they are equivalent. So just by incorporating the subject. But this is not really that desirable if our N is large, but all the Ni's are small. Okay, so if N is large, but N1 to Nn are small. So we have many subjects, but very few observations per subject. Then in this case, fitting separate N regressions for each subject or fitting N regressions, one per subject, is not desirable because you are having too many parameters compared to your sample size. That's just not that will not give you very stable estimates. Then what do we do? Linear Mystefm model is for that purpose. So still, let's take a look at this formula. Look at this formula. So essentially, we have how many parameters? We have beta 01 to beta 0n, n slopes, beta 1 to beta 1n, n intercepts and n slopes. We have two n parameters. So how can we make the parameters fewer while still allowing different individuals, different subjects to have different slopes and different intercepts? So we can add a layer to the model. So what we do is that add a layer of assumption. That is, we can assume beta 0i, these different subjects' slope intercepts to be IID from a distribution with mean beta 0. You can consider this beta 0 to be the common slope for all individuals, and each common intercept for all individuals, and each subject's intercept is just drawn from a normal distribution with beta 0 as the mean. And the variance, let's just say, probably I'll just call that omega 0 squared. Okay, I can assume this. And I can also assume that this slope beta 0 I for individual I, they are IID from another normal distribution with beta 1, the common slope as the mean, and a variance omega 1 squared. So I could do that. You see, by doing so, I essentially reduce the number of parameters from 2n to just 4. So I only have 2 parameters for the intercepts and 2 parameters for the slope. And this is just a trade-off between the two ways. One is that I allow each individual subject to have its own slope, own intercept. And the other extreme is that I assume all the subjects share the common intercept beta 0 and the common slope beta 1. So both are not desirable. One is that I have too many parameters I cannot afford. The other is that this assumption is too simple and not realistic. How can different people have the same slope and intercept, right? So this lies in the middle. I still allow each subject to have a different slope, different intercept, but these may follow a distribution I specify, and that's the normal distribution. So I'm using these two normal distributions to help me reduce the number of parameters. Okay, so that's what we call random effects. So essentially, you see, I can now rewrite the star part as this. Just follow me closely. So I can rewrite star as Yij equals beta 0 plus Xij beta 1 plus delta 0I plus Xij delta 1I plus epsilon ij, where delta 0I follows IID normal distribution mean 0 omega 0 square, and delta 1I IID normal 0 mean omega 1 square. So you see, I just rewrote this by separating beta 0, the mean, from the random part. So you can regard this delta 0I just as beta 0I minus beta 0. Delta 1I just as beta 1I minus beta 1. So I get the common part out, and I just leave the subject-specific part here with mean 0. And this is what we call linear mixed effect model. So this is considered to be the fixed part, and this is considered to be the random part. And of course, this epsilon ij is always a random error. So this is called a random effect. This is the fixed effect. So fixed effect, random effect together, I call that mixed effect. That's why we call it LMM. So you see, essentially, the random effects are introduced to account for subject level differences, but because we have so many subjects, we cannot really afford to estimate one parameter per subject. So that's why those random effects are considered to be intermediate parameters. We're not going to estimate them directly. Instead, we're going to estimate some common variance for them, like the omega 0 square and omega 1 square. So that can save us to reduce a lot of parameters for us to estimate. That's just the practical purpose of doing this. If you do have many observations per subject, you just need to do this, N regressions. You don't need to worry about the linear mixed effect model at all. This is just because we don't have so many observations per subject. So I think this again shows that statistical modeling is always a combination of your goal and the reality, right? You must consider your sample size You cannot really go for the most complicated model with many parameters. Okay, so that's it. And also I want to say that often we are just interested in this beta 1, the common slope, because that means the effect of the treatment regardless of subjects. That's usually of our scientific interest. And that subject specific slope, which is beta 1 plus delta 1i, that is usually not of our interest that much because we want to design a drug that is universally effective. And so subject level differences must be considered into our modeling, but that difference itself is not of our primary interest. Does that make sense? Okay, so you're going to try an example in your homework on problem 2, and you're going to see that if you consider the random effects, the subject level random effects versus you totally ignore them, will give you slightly different answers about your estimates of the beta 1, the slope of your interest. Okay, so I'm going to next quickly show the R package for the one you're going to use for your homework. It's called LME4 package. Okay, so this is the PDF. It's a very detailed introduction to linear mixed effect models. So I'm just going to quickly go over it. It's called LME4 as the package name. So we can quickly go to this figure to give you some sense. So in this figure, you're going to see that here the predictor or feature is the days of sleep deprivation. And the response is the average reaction time. So what we will expect is that the more days of sleep deprivation, the longer the reaction time should be. And we did see the case for many subjects, but it's different from people to people. Like here, for this subject, we even see a decrease in reaction time. So we do want to incorporate those. So you see that here we're just doing this linear regression within each subject. So you see here's a line, here's a line, here's a line. And we have many, many lines. But under the random effect or linear mixed effect model, you are going to do what I just described by allowing the slope to follow the slopes of different subjects to follow a common distribution. And this can essentially allow you to borrow information across subjects. If you recall, that's very similar to much earlier in this class when we talk about that the t-test variance estimation. So we said that when your variance is, when the sample size is too small, you would have a sample variance estimator, sample variance as an estimator for the variance term sigma squared. You will have the sample variance, the pool sample variance with a very large variance itself, which means that it's very unstable. To stabilize it, we give you that Bayesian idea, right? In the Bayesian approach, what we do is that we assume that the sample variance itself follows a prior. And then we want to incorporate that prior to help us stabilize the final estimator for our variance. So that's the idea we introduced before. And here is quite similar. By assuming that different slopes follow a common distribution, you can consider that distribution, the normal with the mean as the common slope and the variance term. You can consider that distribution is like the prior of slopes. But that prior itself involves parameters we don't know. So therefore, we're going to use our data to estimate the parameters in our prior. And that's what we call empirical bias. That's also some concept we introduced before. So therefore, essentially, by doing empirical bias, finally, when you obtain the slope estimates, you are going to have a common slope for everyone. That's of our primary interest. But you can also have a byproduct. That is, you can get a slope of each subject given that prior, the common distribution, and given your data. So you're going to adjust each slope slightly based on other subjects. So what I mean is that using the linear mixed effect model, you're still going to get a slope per subject. But that slope is different from just running regression within each subject. It is also going to be different, the common slope from the common slope across subjects. So what you'll get from the linear mixed effect model will be in the middle of those two types of slopes, the purely specific slope and the common slope. So you borrow information to some degree, and you also use each individual's information. So the formula looks like this. So you're going to do the reaction is your response variable. Your predictor is the days. And this is the fixed effect. And to add a random effect that is within each subject, what you did is that you do days conditioning on subject, put it in a parenthesis. So this specific formula in R, and also this sleep study is just the data set name, data frame name. So this specific formula will allow you to do linear mixed effect model, and it will automatically include random intercepts and random slopes, and also fixed intercepts and fixed slopes. So this is what the result will be like. So for the fixed coefficients, you are going to estimate the intercept as 251.4 milliseconds, and you're going to have the effect of days as 10.47 millisecond per day, right? This is day is the unit of the predictor. Millisecond is the unit of the response. And for the random part, you are going to get its standard deviations. So this standard deviation, if you recall, is what I wrote as the omega 0 and omega 1 for the two distributions of the intercepts and the slopes. So you're going to estimate them as this and this. So this reflects how the intercepts vary across subjects. This is about how the slope varies across subjects. So you're going to get those outputs from the R package. Okay, so that's all I want to say about linear mixed effect models. And let's switch back to my notes. You can see that so another important thing I want to say about the linear mixed effect model, maybe I'll give you the more general formula here. So more generally, we can write yi as equal to xi transpose beta plus, let me just see, zi transpose delta plus epsilon I, or often we have this delta I. So here I just ignore I didn't write out the within group, so I don't have the sub-index j because I'm just writing this out for the whole group. So I from 1 to n. So what I mean here is that you can consider this yi to be a vector that is ni by 1. I just stack all the observations within the group as a vector. Okay, so then this xi is ni by p. Yeah, that's a matrix. And or probably just remove this. Yeah, just get rid of transpose. And then beta is p by 1. And zi is ni by r by 1. And this is ni by 1. So what I mean is that here we consider p fixed effects and delta I random effect, R random effects. And this random effect has this group index associated with it. So this is going to vary from group to group. So I'm going to give you this general notation. And where do we often use it in our bioinformatics? This is random. These are random. It's in statistical genetics. So in statistical genetics, often, for example, we are interested in, let me think of one good example. Yeah, so if we're interested in, say, this yi is some phenotype, okay? Phenotype measured on individuals. And individuals fall into groups, for example, by region. And so in this case, you may want to put that region into this random part. And if you're interested in a particular effect, in the effect of a particular SNP, you can put that SNP as the fixed part. So its effect is going to be assumed to be the fixed part of your interest. And if you consider, oh, probably that SNPs effect is also depending on the environment, and the environment can be considered as the region, which I have the information for individuals. You can put that into the random effects. I think another way I've seen this is that, so sometimes people want to incorporate SNPs, genome-wide SNPs as some predictors to be accounted for. And you may also have another particular gene of your interest. So that gene of your interest should definitely go into the fixed effect. But let's say you have many, many SNPs, let's say 200,000 SNPs in here. So if you consider all of them to be fixed effects, you will have so many slope parameters to estimate for, and that will be too many estimation burden. But what you can do is that you can consider those 200,000 SNPs effects. Those slopes are random effects that follow one common distribution. Then in that case, you just need to estimate the parameter in that common distribution instead of the individual parameters. That can save you a lot of estimation burden. So I'm just giving you a lot of examples to let you be aware that in many cases, we assume a hierarchical probabilistic model for practical reasons. We want to assume a higher layer model to reduce the number of parameters we need to estimate. Okay, do we have questions about this part before we move on? That's all I want to say about the linear model, generalized linear model, and linear mixed effect models. Okay, so that's it. Then let's move on to our next topic. It's the measures of associations. So for this topic, we're going to consider two scalar valued random variables. Let's just say X and Y. They are both scalar valued, and we are interested in their association. So we're going to give a value between those two variables to measure the strength of their association. And for this topic, so it is very useful for network analysis. In network analysis, we often encode our variables as say X and Y as two nodes. Then we're going to decide whether we want to build an edge between them. That's how we're going to do network construction. If the two variables are strongly associated, we build an edge. Otherwise, we don't. So one common application is what we call gene correlation analysis or gene network analysis. In this case, X would be one gene, Y would be another gene, and each gene will have a different expression level at one condition, right? So X, let's say we have 100 conditions corresponding to 100 measurements. We're going to have 100 values of X, and to pair with it, we have 100 values of Y. So 100 pairs. And given those 100 pairs of measurements, how do we measure the association strength of two variables? Intuitively, you would think there is a strong association when we find when X is high, Y is high. When X is low, Y is low, right? That's our intuition. But how do we formalize this? Okay, so in statistics, we always concern about some underlying population, not just the sample we observe. So therefore, here the population would be what? It's actually the joint distribution of the pair of random variables X, Y. While our sample would be observations that are drawn from this distribution. So we denote them as X1, Y1 to Xn, Yn. So you see, your observations must be paired. You cannot do anything with unpaired observations. And If we want to give you a graphical illustration, then what's X, what's the population, what's the sample? So let's say that if X, Y, if we assume they are following a joint normal distribution, two-dimensional normal distribution, let's say the mean is 0, 0, and let's say the covariance matrix, let me just give you one example. So 1, 1, row, row. So which means that their correlation is row and the variance of each is 1. So then we know what it looked like. So let's say here's 0 is 0. Okay, so the Gaussian distribution will be like this. So if you see the distribution is like this, so like a sphere with high density in the middle and the center and less density as you go away. So if you see it's like a square like this, then rho is 0. There's no correlation. And then if you draw data points from it, your X and YN should be like something like this. So that will be your sample. So the red dots will be your sample and the distribution will be your population. And if you have a row that is very close to 1, you are going to have this. So let's say that you have row equals exactly 1. Then the distribution would just be on a line. You see, it's still the center is like here, and you're going to have less and less density as you go away, but you will lie perfectly on a line. That means perfect correlation. So this is rho equals 1. And then you can see when rho is equal to -1, you're going to have the other direction, still a diagonal line. And if you draw sample from it, then the sample will be lying on the line. And the density will be, the higher density will be near the center. So that's what you would expect. So you see, clearly, when the distribution is normal, I already have my first measure. That is called the Pearson correlation. So the measure 1, Pearson correlation, is what's used the most in our practice. So in Pearson correlation, it's defined based on the joint distribution of X and Y. So for this part of the lecture, for every measure, let's think about what's the population measure, what's the sample measure. So the population measure of Pearson correlation has a direct definition, that is the covariance of X and Y divided by the square root of the variance of X times the variance of Y. So if you know the true population, you know how to calculate the covariance and the variance, and you're done. So in this case, in the Gaussian case, you can clearly see that it's just equal to rho. That's the population Pearson correlation. And for the sample Pearson correlation, we just need to estimate the covariance and the variance using our sample. So we're going to replace the population quantities by our sample estimates. So essentially, we can show that this is equal to the summation of xi minus x bar square, yi minus y bar square. And I go from 1 to n. That's the numerator. For the denominator, I'm going to have, I'm sorry, no square, just this. For the denominator, I'm just going to have xi minus x bar square. That's the first term. I take the sum, and the sum multiplies another sum. I go from 1 to n, yi minus y bar square. That's the sample Pearson correlation. And that's what we usually calculate in practice. And one thing that's worth mentioning is that for the sample Pearson correlation, if I denote this, okay, if I denote this as rho x, y, okay, that's the population. For the sample one, I denote it as r and lowercase x, lowercase y to mean the sample. Then the square of this sample Pearson correlation, I call that R squared, lowercase x, lowercase y, happens to be the R squared of regressing linear regression of y on x. So using the x1 to xn as predictor, y1 to yn as response, it is also equal to the R squared of x regress on y. That's very interesting. This is by coincidence. Even though we know the least square regression, so this is the least square. This is the least square regression. Although we know that they are not symmetric, because we know that if we do so let's say this. So we know that if I write yi equals to least square, okay? So if I write this as beta 0 plus xi beta, okay, so if I call this beta 0 half, beta 1 half from least square, then I know that beta 1 hat, okay, let's call this beta 1 hat has this formula. It's actually equal to the Pearson correlation Rxy times the standard deviation of y, I call that Sy, divided by the standard deviation of x. This is the slope, least square slope formula we taught in undergraduate class. Okay, you see it's like this. But if you think of the other way around, if I write xi equals, let me say gamma 0 hat plus yi gamma 1 hat by least square, okay? Then gamma 1 hat would be equal to Pearson correlation, of course, because it's symmetric. So it's still the same correlation, but now it's Sx divided by Sy. Did you see the issue? So these two things are not reciprocal of each other. So which I mean that beta 1 hat is not equal to 1 over gamma 1 hat. While if you want to take the inverse of the relationship by dividing beta 1 hat to the other side to create a linear relationship with xi equals to yi plus times something, you must have that inverse relationship. But the least square estimates do not satisfy this. However, even though the least squares are not symmetric, so it's not symmetric at all, even though that's the case, but it just happened that after we do least square, we calculate the R square. So the R square is defined as what? The R square, let me just say one way, y regress on x, it's just equal to, probably I should put yi hat here. Yeah, that's for the regression. So the predicted y predict xi. So that R square is equal to the sum I from 1 to n yi hat minus y bar square over I from 1 to n yi minus y bar square. So the predicted response variance divided by the original response variance. That's the R square x. And similarly, R square x regress on y would be equal to xi hat minus xi x bar square, xi minus x bar square. So you see, even though these two least square lines are not symmetric, but or they're not the same. They're not the same line. I cannot go from one to the other, but they gave me the same R square. Okay, so motivated by, just as a side note, motivated by the fact that the least square line is not symmetric between x and y. That means which is chosen as the predictor, which is chosen as the response, will give you different lines. Motivated by this, people have proposed an alternative to least square regression, and that is called major axis regression. And this is symmetric between X, and Y. Okay, and very interestingly, just to tell you the truth, this one, the major axis regression, is corresponding to the first principal component if you do PCA on the matrix of X1 to Xn and Y1 to Yn. So it's just that the principal component. So basically what I mean is this. If we have X data here, Y data here, so if your data is like this, then the major axis regression will actually go through the direction of PC1. So it's actually going to be the direction that explains the most variance in your data. And the major axis regression line is symmetric because in the slope, there is no R at all. So in this case, the beta 1 hat would just be Sy over Sx. And then gamma 1 hat is just Sx over Sy. And you can clearly see that beta 1 hat is just the inverse of gamma 1 hat. So you get that relationship you want for the same regression line. But that doesn't hold for the case of least square. So you see, because the least square slope has the correlation as a factor. So whenever X and Y have close to 0 correlation, what happens is that the line will be horizontal. So that means if you do, let me just give you an example. So if your data points like this, looks almost no correlation. If you do least square, that will be the line you get. Okay, that will be the least square line, horizontal. But if you do major axis, you're going to have a line like this. Major axis. But this is not the case when we have a clear, well-defined PC, okay? Because in this case, you may have infinite number of pieces, not rotation. It's not rotation invariant. So you can have many, many directions, but the major axis will always go for this direction because Sy is equal to Sx, then you have a slope equal to 1. So this is just a side note, not directly related to the Pearson correlation, but just something that I think it's good to know. As you know, there are alternatives, not just least square regression. So least square regression is most useful whenever you believe that, okay, the predictors are taken as given. You don't want to change those values, but you believe that the measurement errors are vertical errors just in your Y. So then that's the perfect case where least square should be used. Okay, Pearson correlation, although it's the most widely used measure, clearly we can see that it has drawbacks whenever there is outlier. Because based on the sample Pearson correlation formula, we see that whenever we have an outlier with a very large xi or yi, it will change the Pearson correlation a lot. So therefore, we sometimes want to, and it's also least square as well, is affected by outlier greatly. So in other words, it's not robust to outliers. To address this issue, and also in some cases, we don't want the relationship to be fully linear. We're just interested in monotone relationships. This is for linear relationship, just for your information. In the second case, if we're interested in monotone relationship, and what do? Which means that the relationship is still, when one variable is large, the other is large, when one is low, the other is low, but it's not necessarily linear. So to capture a correlation like this, we have two common options. One is called and we call them rank correlations. So in other words, they are based on ranks instead of the actual values of X and Y. So the first one that's commonly used is called a Spearman Spearman's rank correlation. So what it does is that it converts the values of x1 to xn into ranks. So what does it do? So let me just give you one example. Let's say your xi has value, say 0.8, 1.2, 1.2, 2.3, 18. You see clearly 18 is much larger. It's an outlier. And if you convert it into rank, let's say Rxi, and then we go from the smallest to the largest. So how many do we have? 1, 2, 3, 4, 5. The minimum is going to get a rank of 1. The largest is going to get a rank of 5. This is 4, right? But there is a tie. 1.2 and 1.2 are equal to each other. So they are going to share the same rank because 1 should be 2, 1 should be 3. Then the average will be 2.5. So they receive rank 2.5 and 2.5. That's how we're going to convert actual values into ranks. And then for the sample Spearman correlation, we're going to define S of lowercase x and y just as equal to the Pearson correlation of the rank of x and the rank of y. So that's just a very simple definition. You first convert values into ranks, and then you compute the Pearson correlation. That's it. So you see what's essentially being done is that you are going to compress those outliers by just preserving their rank, but not by their actual values. So no matter if you change 18 to 100 to 200 or even larger, its rank will stay as 1. So the Spearman correlation will not be affected, while the Pearson correlation will change. And for your information, the Spearman correlation also has a population version, but its definition is quite tricky. So we're not going to touch it here because our introduction to the sample Spearman correlation definition is based on rank. But on the population, given a distribution of x and y, how to do the rank is not that obvious. So we're not going to talk about that here. But if you're interested, you can check it out. So previously in our notes, we said Spearman correlation doesn't have a population version, but it turns out that I'm wrong. So I should correct myself for that, but you can check it out yourself. And the second thing is called Kendall's tau. And you may wonder, why do we want to have both? So I would just say that Kendall's tau compared to Spearman correlation is better at handling ties than Spearman correlation. If there are too many ties, you want to go to Kendall's tau instead of Spearman's rank correlation. Okay, so its definition is a little trickier. So it's by comparing two pairs, okay? So let's think of xi, yi as one pair and xj, yj as another pair. You want to compare them, and you define their relationship as one of 3 types. So we call that they are concordant pairs if either case happens, that is xi bigger than xj and yi bigger than yj. So the direction is the same for both x and y, or xi less than xj and yi less than yj. So we call that as a concordant relationship between the two pairs. And of course, the opposite is discordant. So what happens is that you have opposite signs in the two variables. So I would say if this is bigger, this is smaller, or this is smaller, this is bigger. So you have opposite directions, then we call that discordant. And we can have neither. It's neither discordant or concordant. That means whenever you have ties. So if xi equal to xj, when this happens, or yi equals yj. When you have a tie in either variable, you will not call it a discordant pair or a concordant pair. So you see that you can actually leave out the ties out of your consideration in Kendall's tau. And with the definition of concordant pairs and the discordant pairs, then here it comes. So Kendall's tau is defined as the ratio. And in the denominator, it's actually the number of concordant pairs minus the number of discordant pairs. Because the more concordant pairs, the stronger the positive association is between X and Y. The more of the discordant pairs, the more negative the associations between X and Y. So if they are actually roughly equal numbered, then we know their association is close to 0. And the denominator is what? Is the total number of pairs. Let's say on the very, very extreme case, all the pairs are discordant with each other. Then how many are concordant with each other? Then how many concordant pairs would I have? It's actually n choose 2 because we have n pairs. I go from 1 to n. So it's n choose 2. That will be the denominator, total number of pairs. Okay, so you see for Kendall's tau, this definition, its range is from -1 to +1. When all the pairs are discordant, -1. When all the pairs are concordant, +1. And I forgot to say that Spearman correlation also have the range as the Pearson correlation. So it's -1 to +1. And so for Pearson correlation, both its population version and sample version from -1 to +1. Okay, so for Kendall's tau, we also have a not so obvious population version, which again, we're not going to talk about, but if you are interested, you could check it out. Okay, that's the sample version we introduced for rank correlation. I would say in bioinformatics, it is very important to use rank correlation because a lot of relationships are not linear, but they are monotone and thus interesting. Okay, the third type of relationship is what I call functional relationship. So what it means is that X and Y has some interesting relationship like a parabola, but it's not monotone. Okay, so in this case, you see, even if the relationship is perfect, like X here, Y here, if we have a perfect relationship like this mathematically, but if you do the calculation, then you can see that all the three measures we talk about, so let's say call it tau X, Y, all the three measures we talk about will be less than 1. So the R, X, Y, Pearson would be less than 1. The Spearman, X, Y would be less than 1. And Kendall's tau would be less than 1. But if this relationship is indeed of your interest, then you need another measure to capture it, you want a measure to give you a value of 1. So there is a measure called maximal. So I'm going to introduce two measures for this. One is called the maximal correlation. Okay. So its theoretical definition has a long history. So it has been mathematically proposed in 1941 and 1959. Okay, so I'm just going to write them down here. For Kendall's tau, I should say this is from 1938 by Kendall. And so for maximal correlation, so there are two independent proposals of it in the history. But its original proposal was only for the population version. That is, it's based on the joint distribution of X and Y. Okay, it's a mathematical definition as follows. So it's defined for two random variables, X and Y. The maximal correlation is defined as the maximum or the supreme, because here we're actually taking the supreme for two functions over a class of functions. So let's just write sup f and g. So you can consider supreme as a generalization of maximum. Usually maximum is used for a countable of things or a finite set of things, and supreme can be used for a larger set of things. So for possible functions f and g on the transformation of x and y, we want to take the population Pearson correlation, we call that rho, of f transformed x and g transformed y. Take their Pearson correlation and take their absolute value. And then we can see that the maximal correlation by definition, because it's absolute value, its minimum is 0, the maximum is 1. So for example, in the previous case I said, okay, so in this case, if I say the relationship y equals x squared, then what I could do is that I can set fx equals x squared, gy equals y. Then you can see that if I do this, then rho fx gy would be equal to 1 because y equals x squared. So then I would get maximal correlation of x and y equals 1. So maximal correlation has very nice properties. So one is that it is equal to 0 if and only if x and y are independent. While our Pearson correlation doesn't have that property. You know, Pearson correlation, the population Pearson correlation equal to 0 only implies independence when the joint distribution of x and y are normal. Yeah, the normal distribution is only the case when uncorrelated implies independence. But we can always construct examples that are not normally distributed, but two variables that have 0 correlation, but they do have dependence. Mathematically, that's possible. But maximal correlation just didn't give you that possibility. It is equal to 0 if and only if x and y are independent. So that's a very nice property why it was appealing mathematically. But clearly you see that its calculation is not trivial. How do we find the proper f and g to transform our variables, to transform our data, so that we can compute the maximal correlation on a sample? So on the sample level, the calculation of maximal correlation wasn't feasible until the 1980s. So that is something we called an algorithm as alternating conditional expectation. I think the reason why this was not proposed as a numerical algorithm earlier was because of lack of computing resource. So before we have computer, we cannot really do this by hand. So that's why it's not even an option. But with computer, we can do a lot more. So this ACE algorithm, I think it's definitely very good to know. It was proposed by Bryman and Friedman in 1985. So Bill Bryman was the person who invented many famous algorithms like the CART algorithm for classification tree, the random forest, and the boosting. So he has and the random forest for ensemble. So he has introduced a lot of those important things into the machine learning. And so this is his other contribution about the calculation of maximal correlation. So how does it do? So let me just give you a very brief preview before we talk about next time. So it tries to convert the problem of maximizing the correlation into another problem of minimizing the squared mean differences between fx and gy. So it changed the problem from a maximizing problem to a minimizing problem, and also changes the objective from correlation, absolute correlation, to the expected squared differences between fx and gy. Okay, So we will stop here and then we'll continue our discussion about the functional relationship next time. So hopefully we will be able to finish our measures of association in next lecture. Then starting from next week, we're going to talk about some sampling algorithm as the last part of this class. So if you haven't signed up for your group project, please respond to Wenbin's message as soon as possible so that you will receive your presentation for week 10 very soon. Thank you.